Okay, so we're going to start looking at differentiation. So thinking about differentiation in broad terms, or like the basics of differentiation, we're thinking about the derivative. So your derivative is essentially allowing you to find the rate of change, or like the gradient of a function at a particular point. So yeah, graphically, this is what your gradient is. So the gradient of the tangent at that point. So hopefully you guys remember that the tangent is a line that intersects your function exactly once. So that's what this red line is. And if we're saying that this is our point of interest, the derivative here, we're looking for the gradient of the tangent when it hits that point. Okay, so that's pretty much the big thing you need to know about differentiation, is like, what are you actually trying to find? The reason that that's important is because if you understand what you're actually trying to find and like what the numbers you're doing, I guess like graphically mean, then it becomes a lot easier to do your applications of differentiation, because it's much easier to see how these things translate into like a real life sort of situation. So yeah, big things to remember here is that your derivative is allowing you to find the instantaneous rate of change, okay? Make sure you remember it's instantaneous because it's only at one specific point. Like, it's not the rate of change, from point A to point B. It's at like the rate of change at a single point. And that graphically, that means that you're finding the gradient of a tangent. So looking at the basics again with our differentiation, important to remember, all of these things are on your formula sheet, so like, don't stress about trying to remember them. More important that you just remember how to use them. I think people in maths get a little bit twisted and get a little bit like confused trying to remember all these different rules, but all you have to do is know how to use them. You don't have to remember the rules themselves. They're all on your formula sheet. So we've got the power rule, which is the very, very basic rule of differentiation. So we're looking at the derivative of x to the power of n. What we want to do is bring n down the front, keep our x the same, and we do n minus 1. So quick side note that this will work when your n is a negative number or a fraction as well. Doesn't matter what your n is, you can use this rule. And that's just like your basic rule of differentiation. If you had something like, I don't know, like 4x squared, you'd bring the 4 down the front, so you'd have 4. You'd bring the 2 down the front, so you'd get 4 times 2x, and then 2 minus 1, and you'd end up with 8x as your solution. So it's just like your basic differentiation stuff, really. Then looking at your basic trigonometric differentiations, the derivative of sine x is cos x, derivative of cos x equals negative sine x, and the derivative of tan x equals sec squared x. That's really all there is to that. They do get a little bit more complicated when you start putting fx in there, but we'll have a bit of a look at that later on. Yeah, that's really all there is to it. It's important to remember your differentiation stuff and to be really on top of it, because it will help you with your integration. I think one of the big reasons that people struggle with doing integration in Year 12 is because they didn't understand differentiation to begin with. And if you guys know anything about integration, you know it's the reverse of your differentiation. So it's going, from what you've differentiated back to what the original function was. So hopefully you guys get a good understanding through this lecture of your differentiation and what's important about it, and then you'll be set for your integration as well. So some more of the basic rules that are used really commonly is your e to the x. That does come up fairly commonly, something that you do need to know, that the differential of e to the x is just e to the x. And then a little bit of a harder one. For me in Year 12, these were my least favorite differentiations to do. I hated logs and exponentials. I don't really know why, I just did. But these rules are a little bit harder to remember, I think. Or harder to remember that they exist. So we've got the differential of a to the x. So that's where a is any base number. So let's say you might have 3 as your a. And then x is just in your exponential here, you just have to have a pronumeral. So that could be, 3 to the x, that could be 3 to the 2x minus 1, that could be let's say like 6 to the power of 2a, like it's just going to be a base number and a pronumeral in your exponential is essentially what this is trying to get at. And so when you've got something like that, what you want to do is you're going to have ln a, so whatever your base number is ln of that number, and then multiplied by whatever your original function was. So like let's say we had 3x, or 3 to the x, we'd end up with ln 3 times 3 to the x. And that's all you have to do for the exponentials. So yeah, if you're like me and you don't like your exponentials, just remember that they exist and then you're in your formula sheet, and whenever you see something that has a pronumeral in the power, just know you have to use one of these two rules. So then we've got logs. So log differentiation is something that a lot of people forget that you can do. So it's important to remember that you do know how to differentiate just a base log of whatever, as well as ln. So yeah, a lot of people forget that those exist. So just, I guess, remember that they're there and that you do know how to differentiate your logs. But for ln x, the differential is 1 over x. This does get a little bit more complicated when you've got like ln f of x, but for now, we'll just keep it as ln x equals 1 over x, and we'll look at the little bit more complicated version in a minute. And then for differentiating any other log, so anything that's not base e, so log 2x, log 10x, log 27x, whatever, we're going to have log ax equals 1 over ln of your base, or your a, multiplied by x. And those are the very basic differentiation rules that you need to be aware of. The other thing you really need to remember is that these are base forms, but from those base forms, we've got the chain rule. So whenever you have a function that's within a function, you differentiate the same way, but you also have to multiply the result by the derivative of the function inside. So this applies no matter what you're differentiating, whether that's a log, a trig function, just your basic differentiation, an exponential, whatever. If you have a function within your bigger function, so you've got some brackets within your function or something like that, what you need to remember to do is that you differentiate the whole thing first. So you've got gu dash of fx, and you have to remember that you need to multiply the entire derivative of the function by just the derivative of what's inside the function. So you do g dash of fx multiplied by f dash x, and that will give you the correct answer. So this applies every single time, no matter what you're differentiating. You have to remember that if you've got a function within the function, that you then need to do this. We will have a look at some examples later on, so don't get too stressed if that's confusing you. But yeah, the chain rule is super important. No matter what you're differentiating, every time you've got to consider, do I have to use the chain rule here? Okay, so looking at the base forms seems fairly straightforward. And I don't think it actually gets too much more complicated, but you do have to remember, like, what do we do if there's not just x? So for example, what do we do if this is not just x? What if inside the brackets it's like 2x plus 5x squared? What do we do then? Then you get some, I guess, more complex rules to use. So this is the, I guess, more complex rule from your basic differentiation. So what do we do if we have a whole function here and not just an x to the power of n? So then your differential, you bring your n down, multiply it by the derivative of your fx, and then you do your normal fx to the n minus 1. Fairly straightforward, same principles apply. You would have learned this in year 11, so I won't spend too much time on it. Same with these, you should have learned these in year 11 as well. So we've got y equals sine fx, the derivative of that, you find the differential of just your fx, bring it to the front, and then multiply it by cos fx. Same sort of principle applies with these two. Find your differential of your fx, Just like how you'd have negative sine x, you do negative times your differential times your sine fx. And then again, same principle for tan. Find the differential of your fx here, bring it to the front, multiply it by sec squared of fx. Okay, those ones you should have learnt in year 11 as well. So I won't spend too much more time lingering on those. These ones you may not be so familiar with. I'm pretty sure you do them in year 11. At least your school, I think, should have done them in year 11. But they do tend to confuse people a little bit more. So we'll spend a little bit more time on them. So they are following the same principles as the base forms that we looked at. If we have e to the fx, all we want to do is bring down the differential of our fx, and then we do the exact same e to the fx, because that doesn't change. All we need to do is remember to bring down our differential of whatever is in the power. Okay. Then if we have y equals ln fx, all you need to do for this one, remember that you're not going to have any logs in your final answer. Unless your fx has logs in them, but usually there's no logs in the final answer. All you need to do, differentiate your fx, put it on the top of the fraction, and on the bottom, just put fx again. So you'd end up with f dash x over fx if you're differentiating log e or ln. Now these two, again, my least favorite. I don't know why I didn't like them that much, but I didn't when I was in year 12. But yeah, so if we've got y equals a to the fx, very, very, very similar principle. We have our ln of a, so whatever our base is, ln of that, multiply it by the differential of fx, so f dash x, and then multiply it by our same a to the fx. Okay, so really, really similar to the base form. And then finally, we've got, if you're differentiating y equals log a to the fx, you're going to get the differential of fx on top all over ln a times your fx. So with these here, they are all on your formula sheet. So pretty much all you need to know is how do you actually use them. Okay, so don't stress if it all seems a little bit like, oh my gosh, how am I going to remember these things? Because you don't have to. All you have to know is, okay, I need to differentiate a sine equation. Let me look at my formula sheet and see how I do that. Or, I need to differentiate an exponential or a log. Let me look on my formula sheet to see how I do that. As long as you're familiar with where all the different letters go, so you sort of know like this A is going to come here, and this is fx, and that's here, and the differential here. As long as you're sort of familiar with all the letters go, practice with them, and you will just get really, really familiar with how to answer the questions. With differentiation, there's not so much that they can ask you, because your differentiation rules are your differentiation rules. So pretty much how they make these questions more complicated is by, embedding lots of things within one question. So let's say with differentiation, the first thing you have to do is simplify the equation, or, with trigonometric expressions, a lot of the time you have to rewrite the expression. And then from there, you can then do your differentiation. So yeah, with sort of differentiation questions that you're looking at, and you're like, damn, I don't think we actually have a rule to be able to answer this question. First, see if you can simplify it, if you can, rewrite it. So let's say they've given you like a reverse trigonometric equation. So let's say like they've given you like sec of 2x squared or something. Firstly, okay, how can I rewrite that into one of the trigonometric equations that I do know how to differentiate? And then you can go from there with your differentiation as well. Okay, so just with these rules, just please remember that they are on your formula sheet. You don't have to remember them. If you're ever uncertain in your exam, when you're doing your homework, whatever, if you're ever uncertain about what the rule is, check it. And the other thing going along with that I can give you as a tip for this is when you are doing your exams, rewrite the formula on your working out page or your test page or whatever. Because I found that in my cohort, when we were doing our HSC, our exams and things in the lead up to the HSC, a lot of the time people would make mistakes from doing the wrong formula. So, they'd be looking, one line up on their formula sheet or one line down or something. And because the marker didn't know what they were doing, the answer was just wrong. Okay, so rather, if you write down the equation, number one, you can double check that you've got the right one, because if you're actively trying to write it down, you're going to pick up on the fact that you've got the wrong equation. But two, even if you do have the wrong equation, your marker can at least see what's gone wrong. They can be like, oh, they've done, the wrong trig equation, or they've done the line above where they should have, or something like that. So it'll be easier for the marker to give you marks, so they can sort of see what's gone wrong as well. So writing the actual equation that you need to, or like the formula that you need to use on your sheet, just helps reduce those like human error mistakes in your exams. So then the other two rules that we want to look at with differentiation, don't you guys worry, I have not forgotten them. What happens to be a lot of people's favorites, or least favorite, the product and the quotient rules. So product rule I find much easier than the quotient rule, because it does not matter which order you do it in. It could be u dash times v plus v dash times u. Or you could do that the other way around, and you could have u times v dash plus v times u dash. Doesn't really matter with the product rule. Doesn't matter which one's u, doesn't matter which one's v. Just have to have one as u, one as v, and put them in there at some point. So yeah, I typically do it alphabetically. So my whatever's first, I do as u, whatever's second, I do as v. And then I start with u dash times v plus u times v dash. So yeah, that's your product rule. Super important to remember whenever you've got two terms that both have a pronumeral in them and they're being multiplied together, you need to use your product rule. I think the product rule usually people find harder to pick up when you need to use it. Then the quotient rule, I think the quotient rule usually is a little bit more obvious, because they've put them in there as fractions. So say with like your quotient rule, you will have like a literal fraction with something on the top, something on the bottom. So it's really easy to pick up that you need to use the quotient rule. Product rule, not as clear cut to like see, I guess like physically see that you need to use it. So you just have to remember, anytime you have two pronumerals being multiplied together, you need to use your product rule. So yeah, that's the product rule summed up. There's not a whole lot to it. The hardest part about the product rule is knowing when to use it. So yeah, just remembering that anytime, I cannot stress this enough, anytime you've got two pronumerals being multiplied together, you need to use the product rule. Sometimes they'll make this really obvious for you and you'll have like two sets of brackets being multiplied together. Other times it won't be as obvious. It'll just be things, like, say if you had like 2x squared times 3x squared, that would be needing to do, actually with that one, you could probably just multiply them together. But theoretically, you would need to be using the product rule to do that. So yeah, that's the product rule. And then you've got quotient rule. Like I said, it's a lot easier to like physically see and pick up that you need to use the quotient rule in comparison to the product rule. So you'd have something on the top, something on the bottom. Have to remember with this one, super important the order that you do them in, and it's super important what you assign as u and what you assign as v. So whatever is on the top of your fraction is going to be u, and whatever you're dividing by, or whatever's on the bottom of your fraction, is going to be v. Super important that you do allocate those correctly, and important that you write this in the correct order as well. Because when you're doing subtraction, it does actually matter which one is first and which one is second. So we always want to start with u dash times v minus u times v dash all over v squared. Yeah, that's really all that there is to the quotient rule. I can't really explain too much further on that. So yeah, these are also in your formula sheet, so you don't have to remember them. And it is also in your formula sheet the correct order that you need to do your quotient rule in. So if you do ever get confused of, to do u dash first or v dash first, check your formula sheet. It's on there. It's worth taking the extra 10 seconds to look on your formula sheet and make sure you've done it correct, than to be second guessing whether you've got it correct. Okay, so yeah, I guess if another just little piece of advice, always check your formula sheet. I don't know why some students don't like to check it. They think it's going to waste time. They think they know it, but it is worth the extra 10 seconds it's going to take to look at your formula sheet and find the correct formula. Trust me, it is always going to be worth the 10 seconds. Okay. So